Now, we are discussing about the free settling velocity at the terminal condition, that is the terminal free settling velocity of a particle. Now, we discussed about the Stokes actually the Stokesian particle settling velocity. There is another scientist who is well known to everybody. It is known as Newton's equation. Now, this region, that is Stokesian region, is also known as laminar region. That means, it has hardly disturbed the your flow of the fluid surrounding the particle. Now, this is applicable for your bigger particles, when the particle mass, that is the inertia, dominates over the viscous forces or the viscous stresses offered by the fluid itself. So, that is known as Newtonian region, or we call it the turbulent region. That means, it has given the your AD's formation and all this happens, and it is the disturbances, total utter disturbances in the fluid medium it has created. So, Newton has proposed that when the RE is greater than 750, look at Stokesian region less than 0.1 and this is RE greater than 750, the CD is no longer dependent on Reynolds number, it has got a constant value. So, beyond a certain particle size, it does not matter how much of disturbances it has created, the CD, the drag coefficient remains constant, it has got a value of 0.445. Although many literature they debate on this third decimal point value, and that third decimal point value difference makes a lot of a difference in your calculations, but let us stick to this, that is CD is equal to 0.445, or we can assume that CD is equal to 0.5, approximately close to 0.5. So, if I put this value of 0.5 into the basic equation of the settling velocity, that is the general expression what we had already discussed, then the equation, final equation becomes that V t is equivalent to, I am not writing equal because I am not sure that whether you can really approximate it to be 0.5, but generally we do it for simplification of the expression, that is V t is equivalent to 3 d p g rho p minus rho f divided by rho f to the power 0.5. So, we got the expression, and now what could be the particle size of this? I again give this reference of quartz density particles, that is particles who are having a density of 2650 kg per meter cube. It is close to particle size more than 5 millimeter. So, this is basically, so we are in the range of, so below 50 micron we have got a Stokesian region, above 5 millimeter size we can use this equation for quartz density particles for Stokesian, for Newtonian particles. But what will happen to those particles whose Reynolds number is in between this? And then there is another condition, is that how do we find the Reynolds number, because here also that terminal velocity term is there. So, these are the two questions we have to answer, because neither we know the V t nor we know the Reynolds number, and then in between Reynolds number, what would be the settling velocity equation even at free settling conditions for spherical particles, we do not know. So, that is what we have to discuss. So, if you look at the literature, although I have written here the single equation not available, but this is not correct statement. What I try to mean with this, that there is no reliable single equation which is available. Reliable means there are so many equations, but available in the literature, but all these equations, they have got their own limitations. So, there is no universally acceptable equation. So, please read this statement carefully, that no universally acceptable single equation is available for predicting the settling velocity of particles in the transitional region. Like, we do not have any controversy about the Stokesian condition, we do not have any controversy with the Newtonian region, but we have many equations proposed by many stalwarts in this field, but still all individual equations, they have got certain limitations. So, now the question is, how do I select them, and when we have many equations, on what basis I will select that which equation is the most suitable or most appropriate. So, to solve this problem, in 1940, the two scientists Lappel and Seyfert, they proposed a curve. What is this curve? This curve is known as standard drag curve. So, what they did, they reviewed all the proposed equations by many scientists, and they have reviewed it very carefully, and they have selected the different relationship proposed by different researchers for different Reynolds number region, because someone proposed that the CD value as CD is having a relationship with Reynolds number which is applicable from this Reynolds number range to that Reynolds number range. But actually you have to cover the entire range of your Reynolds number. So, when they have proposed this curve, that is, if you plot the particle Reynolds number versus the drag coefficient proposed by different researchers, you will find a typical shape of this curve. Now, this curve is known as the standard drag curve. Why it is called standard drag curve? Now, the chemical engineering fraternity in particular and fluid mechanics community at large, they have accepted that this curve is let us consider that this curve is a standard one based on which we will compare the different models. That is, what is, if I propose a new model for this settling velocity, I have to say that what is that CD and RE correlation I have used, and I have to prove that that CD and RE correlation appropriately fits into these or gets superimposed on top of this drag curve. Otherwise, the predicted values may be questionable. So, now many attempts were made after that, that is, to propose a single equation to predict this standard drag curve, but because of this typical shape of this curve, there is no single equation available which can predict this curve perfectly. And that is why I said that a single equation may be proposed by someone, they may be say quite good when you are dealing with the Reynolds number range within this region. That means, they work well if your particle mass varies from this to this. That means, if your size and density relationship brings the particle Reynolds number range within that range. So, that means, my CD and RE should be having this type of trend, but that equation I cannot apply it when I am dealing with much bigger particles which are having a Reynolds number of this range, or maybe for very smaller particle, very finer particle, very fine particles which follow this range, because and that is the limitation what I was mentioning, that for different equations they have got these limitations. Even there are equations I will name some of them. That is, they are very famous equations, they are well referred to that. That is Kleeman, Concha and Almendra. Concha and Almendra's equation probably are frequently used by the mineral processing community. Then Jigrang, Sylvester, Tartan, Clark, even Haidar Levenspiel, they all propose single equations based on drag curve, that is the entire drag curve. But if you look at the basic correlation they have used on CD and RE, they are not able to get superimposed exactly on top of that standard drag curve. And possibly that is the reason that if I have a synthetic particle size or density, and if I try to predict the free settling velocity of those particles at different sizes or different density combinations by using these models, ideally if they are fundamentally right, all the equations, then ideally the predictions irrespective of the models, they should have the as identical predictions. But if you try to predict them, you will find that there is a large difference between the predicted values when you use the equation of different equations. So, again the question comes, which equation should I use? I personally believe that I must use that equation which can predict the standard drag curve much accurately. So, for that, if you see that this Concha and Almendra's equation, as I said that it is frequently used and it is a very it is a really a robust equation, and the basic equation, the basic model they have used while formulating this model by Concha, Professor Concha and the student Almendra, they used the Abraham's equation for CD and RE correlation. And if I plot that CD and RE correlation, I see that we can see that the blue lines they are showing the Abraham's equation, and red line is your actual standard drag curve, that they get almost superimposed up to this region, but they start getting deviating even when the Reynolds number is going in the much higher side. Even with the naked eye, we may not see the differences between this, the blue and the red values, but I will show you that even with this, even with this small differences, how your predicted values can differ to each other. So, before I show you that, let me show you that another, it is not a single equation, it is, there is a classic book on bubbles, drops and particles written by Klieft, Grace and Weber. There you will find that they have proposed a set of equation, not a single equation, a set of equation where you have got the CD and RE correlations at different Reynolds number range. They have even modified the Stokes equation, they have modified the Newton's equation based on the findings of many researchers. So, you see that it starts from less than 0.01 Reynolds number and it considers up to 10 to the power 6, Reynolds number 10 to the power 6. And they are all having this type of relationship. They may look little bit complicated, but they are very simple when you look at closely, because the W is equal to log 10 RE. So, you have to replace the values here. So, you get a correlation of CD into RE, CD and RE. Now, the question is, can we not use this set of equation, because this, if you try plotting this CD and RE correlation with this set of equations, you will see that probably it gives the best fit so far to the standard drag curve than any other equation. So, what we are trying, that is, can we not use this set of equations for predicting the settling velocity of terminal settling velocity of the spherical particles into a stagnant fluid medium. So, for that you see that everywhere your C d and R e is there, and I said that for R e also there is a V t term. So, you have got your two unknowns, you have got say two unknowns and a single equation. So, it is impossible to find a solution. So, what do we have to do? We have to go for an iterative technique to use this for finding a solution for V t. Now, for any iterative technique, you need some convergence criteria. So, what could be that convergence criteria? You may be thinking that this is an introductory course. Why I am discussing this topic at that depth? The reason is that there will be many participants who are coming from the industry, and to educate themselves or to fine tune their knowledge, so that they can make some differences after this course to their respective plats. And for the students also who are taking this, you may join the mineral processing industry in near future, and this aspect, that is your movement of solids in fluids in conventional literature, in mineral processing, in standard textbook, they are not that given priority, or they are not given that much of emphasis because of the complexity associated with this. So, but as I said that we are dealing with water based processes. So, this is a fundamental prerequisite that we must know how to calculate the settling velocity of the particle into a fluid medium, and we must be aware that what are the limitations of these equations, and what are how much of error we can have because of your say selection of a particular equation, and this will not help in optimizing our process conditions quickly, but also in better designing our equipment, in better selecting our equipment for a particular process. That is why I am giving so much of importance to this topic. So, you may not have to remember all these equations. I may not ask you very difficult questions based on this, but I thought that it is my responsibility to tell you that what are the difficulties associated, and where we stand, and how we can utilize this knowledge for fine tuning our processes. So, for this iteration process, we are looking for a convergence criteria, and there is one number that is called the BEST, BEST is the name of a scientist. It is available in fluid mechanics literature. I am not getting into that detail what is that number is, but I have used it, we can use it as a convergence criteria. Why? Now, the best number is defined as 4 rho f, rho s minus f, rho s is the density of the solid, rho f is the fluid density, g is the gravitational acceleration, dp is the particle size, and mu is the fluid density here, mu f it should be. So, that is how it is written, the base number is defined as, and if you convert this equation in terms of C d and R e, you can have this is equal to C d into R e square. So, now you see that these are the input, these are the prior information we can easily have about my particle and about the fluid, because if I know the fluid and if I know the temperature, I can easily get to know the rho f and mu f, and particle size I can measure, particle density I can measure, and I know we all know the gravitational acceleration number. So, this is equal to C d into R e square. So, how you can use this set of equations? Now, before I go to that how you can use it. So, if you plot that set of equations, you see that it can get superimposed on top of the standard drag curve. That is your red one is the standard drag curve, and this is what I have said, that this is the Clift et al.'s correlations. And you see that at least it is taking that shape, but it is not yet getting superimposed on top of this. So, maybe someone in your future from you will come up with a better equation to predict this standard drag curve. But as far as I am concerned, this is the best available relationship which can predict the standard drag curve. Now, what we can do, if you have a little bit exposure in writing computer codes, so you can write this in MATLAB or in any other language. What you have to do, that is, your first input values will be that particle properties like your size, density, and the operating temperature, because if I know the temperature, if I know the fluid, I can get to know the fluid density and viscosity. And once I know these parameters, from that best number correlation, I can get to know that what is the best number for that solid and fluid when we have the interactions. So, now what we can do, we can put a small initial value of R e, because we do not know the R e, we do not know the Reynolds number of the particle, neither we know the drag coefficient. We try to find out that which correlation fits well, because we have got 10 different sets of equations. So, you put a very small R e value. So, if it is a very small R e value, so R e say suppose less than 0.001. So, then we can calculate the drag coefficient value based on the first set of equations. So, that means, if my R e is very small, I can use this equation to calculate the value of C d, and once I know the value of C d, I can go back to the original equation or the general expression for terminal settling velocity of a spherical particle, and I can easily get to know the settling velocity of that particle, that is the V t. Now, after putting that your very small value, I get to know the C d value from this set of equation. Now, once I know the C d value, so I know the R e, say suppose R e is 0.0001, and I know the C d which is being calculated based on this equation. So, now I can calculate what is the value of C d into R e square. So, if that C d into R e square, so that is equal to best number. So, from your assumed value, that is your initial value, what is the C d into R e square you are getting, and if your approximated value is accurate, then it should be equal to the value of best number which you have calculated based on these input values of particle properties, that is size, density, and the fluid density and viscosity. So, if the difference between this, that is your best number which you have calculated based on the your assumed value, and is and the calculated value of best number based on the particle size and density and the fluid density and viscosity, if they tends to 0, that means the difference is negligible, then we say that we conclude that my approximated value of R e, that is Reynolds number, is correct. And if not, then what we can do? We can go back, that is how we try to do your basically iterative program, that is we call it iteration, and you can practice it if you have exposure in computer programming. So, then what we can do? We can put an incremental value of that initial value. So, suppose my initial approximated value of R e was 0.00001, we can now increment it with the value of, let us say, 0.00002, and then again we will redo this calculation and we will try to see that whether my predicted value and the calculated value of base number, the difference between that is close to 0. So, we keep on doing this unless and until they converge, the convergence criteria you can set, that is how much of what is that value, the difference you will consider that is your convergence criteria. So, once it gets converged, so that means that is the correct value of your particles Reynolds number into that fluid medium. So, once I know that, so we can finish the iteration and we can get the value of drag coefficient, and then based on that drag coefficient we can calculate the free settling velocity of the particles. So, you see that what are the difficulties even in predicting the free terminal settling velocity of a spherical particle in a stagnant fluid medium. Now, this is what I have tried personally, you can also give it a try, that suppose you assume that there are some synthetic particles of different sizes and they are quartz particles of, that means the density we know 2650 kg per meter cube, and if I try to predict their settling velocities at different sizes using the Concha and Almendra's equation and the Clift's and the equation based on this your say set of equations proposed by Clift et al. So, I have named it as Clift's your model, and based on that iterative technique you will find that up to a very fine size range, that means up to 200 micrometer size, they are say matching with each other, they are agreeing with each other. But as the size of the particle increases, their value differs, they starts differing. So, now you see that even at this size around 500 micrometer, the predicted values are having a difference of almost 10 millimeter per second. So, now the question is which equation I should use, I leave it to you, but my personal recommendation would be that if you have some knowledge in computational skill, in computational your say coding, then you can write an algorithm and based on that Clift's set of equation, and that would be I think my personal recommendation. You may differ, different people may have different opinion, but I would say that I will go for that because the it can better fit, it can better predict the standard drag curve. Now, this is about spherical particles. Now, in reality we said that we hardly get spherical particles. So, what will happen with the non-spherical particles in Newtonian liquids? I am not going into Newtonian, non-Newtonian fluids. I say that a non-spherical particle in a fluid, stagnant fluid medium. So, we have already discussed, when we discussed about particle shape, that what are the intrinsic difficulties in defining the particle shape, and ultimately we had concluded that the particle shape can be defined in terms of sphericity, where sphericity is equal to the defined as surface area of equal volume sphere divided by surface area of particle. We had a detailed discussions on this, so I do not want to repeat that. So, if you look at, and these examples also there I have shown that your sphere has a sphericity of 1 and any particle deviating from spherical shape, it will have a sphericity or much lesser than 1. So, for cube it is 0.81 and cylinder based on its cylindrical particle based on its orientation, they have got different numbers, and these numbers I have got it from literature. And smaller the value of psi, greater the deviation from spherical shape, that means they are more flatter particles. Now, there are some popular correlations for predicting the settling velocity of your non-spherical particles into a stagnant fluid medium. Some of them are highlighted here. One is Haider-Levensspiel. I do not want to trouble you with the complexities of these equations, but I would like to highlight only one thing, that you look at that they are simply empirical in nature. So, that means these values you see A is equal to 0.181, B is equal to 0.646. So, when you try to use these equations, you must look at that those original publications, that what are the limitations of this, for what are the particle types they have used while proposing these equations, because that is the main limitation of any empirical model. There are certain other models which are very popular, that is, one is Ganscher. Again you see that this is again a empirical equation, a very complex one. A chain, that is also an empirical equation. Now, which one is the best? So, this question was asked by Professor Chabra of Indian Institute of Technology, Kanpur, and in one of his publications in the late 1999, he published this in a Powdered Technology journal, and he had shown that with the large databases he has used 1900 databases based on some experimental data. These are it's a very carefully measured data set, and he has tried to use this Haider-Levensspiel model, Ganscher model and chain model. He has shown that although the mean error are within 20% in most of the cases, 21.5, 16.3 and 23.5, but what he has highlighted, that look at the maximum errors, it can go up to 276%. So, now this is what is telling us that we should be very careful about using these equations for non-spherical particles, because you never know that whether you are within that maximum error zone or not. So, you should try to verify it with some kind of your measured data set. So, that is my suggestion to all of you. So, we will continue this discussion for the concentrated systems in the next lecture. Till then, thank you very much.